All right, so there's our voltage divider. 79 volts is the power source. RL load A is 9 volts, 3.75 milliamps. R load B is 3 volts, 3 milliamps. R load C is 33 volts and 22 milliamps. R load D is 50 volts at 31.25 milliamps. And again, we want to find how much our bleeder current is and the values for R1, R2, R3, R4, and R5. Let's take this guy, shrink him down. Okay, let's bring him over. Happy music. Okay, Morgan. First set of voltages that you would like to find. Okay, R2 is why? .33 volts. Because again, they are directly in parallel with those loads. So those are the voltages across those components. Okay. Zach. Voltages for R1 and R4. Okay. Okay. Correct. Zach, you're up again. What's the voltage across R5? 20 volts. And how did you get that? Okay. So again, Kirchhoff's voltage law. No matter where we go, we have to equal these values out. Okay. That's the other thing we'll do is we'll go through, once we get this solved, I'll take you guys through a Kirchhoff loop. And we just want to make sure that no matter which way we go, it's going to equal 0. Okay. So we have our voltages across all these guys. Now we need to start solving for our currents. So we'll put our nodes. So we got node A, node B, node C, D, E, F. It's a galaxy. It's a galaxy one. It's okay. So those are our nodes. Okay, Max. Do you want to go after solving for the current pass, or do you want to go after I bleeder?
I bleeder.
I bleeder?
Yeah. So I just by looking at it, I could see that the bottom one, RLC and RLC were bigger.
Okay.
So I added those together, which got me 53.25 milliamps, and I know it's going to send it out to 5.2.
Okay. And because you're taking your current from this side, it's going to go across R3. And how much did you say?
5.2.
Okay. I agree with that. There's another way, like I said, keep that in mind. We'll also come through as we're solving the currents as if we didn't know that, and we could solve it at that point as well. Okay. Everybody okay with where we're at so far? Haven't completely lost anybody? Okay. Yes.
He's not on the spinner.
Is he not on the spinner? How did that happen? That is a very valid argument.
This makes a lot more sense than what we did.
When you're in the car.
Yes.
Whatever understanding between Tuesday and today, it's like black and white. I know it's going on.
I don't, so you don't really.
Thank you for bringing that to my attention. I'm sure Dylan is not excited about that. Okay. Spencer. Okay. Where do we want to? Were you caught up to this point?
Okay, so I'm thinking at this point we calculate the current for node E.
Okay.
So there is 31.25 milliamps going into node E,
Into E.
and there's 3.75 milliamps going out, which means we need 27.5 milliamps going to E to make the top happy.
Going out. Because we have 31 going in, we have 3 going out, we only have one more connection. Yep, so that one has to go out to keep Kirchhoff happy. Okay, so that satisfies node E. We have all the connections going in and out of there. Okay, everybody okay with how we got that? Again, we have 31 going in, 3 going out. We have to have the 27 going out as well to keep it as a net zero. Okay. Dylan. There it is. Okay, current block or current node D. Yep.
We have 3 going out. So we add 1, 2, 27.5. We get 49.5.
Okay.
Minus 3. We're left with a surplus of 46.5. But 46.5 going to the left.
Yep, heading out of that node. That's the way the cookie crumbles. Okay, this is the way. Dang it, I should be using that phrase more often in here. Any questions about that? Okay, so now at this point, one of the things we could look at is look at where these currents are going. So if I didn't know that my bleeder current was here, and I was still looking to determine which one is going to be my bleeder current, this current that I have here, does it contain any load current? Any current that has flown through a load? Yes. Because we have this much current coming through. So it has to turn and go this direction. The voltage behind it is going to push it that direction. So when it gets here, we know that the current going through R2 contains load current. So if it contains load current, then it is not bleeder current. Bleeder current is only current that never ever sees the load. For the 46.5? Okay, so we have the 22 coming into the node D from the load C. We have 27.5 coming in from node E. We have 3 milliamps that's leaving. So if we combine all those together, we end up with the 46.5 milliamps that's going into the node. Or the 49.5, sorry. Yep. Everything that's going into a node and everything that's going out of a node. So we have 46.5 leaving that node. And then, like I said, it's going to turn and go this direction because the voltage is going to force it that way. And so if we have that, we know this is not our bleeder. So again, reaffirming that down here is our bleeder current. So now we're going to look at node C. Max.
Wait, didn't we just do that? Oh no. Okay, so yeah, we're just gonna add the voltage coming across R3 and the voltage goes or the current going across R3 and the current going up from between B and D, and that was at 50 and 118.
That's not what I clicked on. Okay, so with this ground, it is just there as reference. No current will flow to it. Because also, if you think about it, there's no other connection for it to go. There's no other connection off the schematic to where that would flow to. So there's no current flow that direction. It's an open. We have 5.325 milliamps coming in. We have 46.5 milliamps coming in. The only other path we have is up this direction. So we add them together and we get the 51.825 milliamps. Let's see. Any questions about that? You good there? Okay. Jessica. So now we can go a couple of different directions. We can jump down to node F, we can jump up to node B, or we could even, one of those two places. Where would you like to go from here? To B? Okay. So at B, we have what current's going where? Okay. Yep, the 3's coming in. That's all we have. So we have one direction left. So how much do we have and what direction is it going? All has to go out. That's at node B. Okay. So again, we have the current coming up through R2. We have the current coming up through our load B, converging at this point. So 51.825 and 3 gives us 54.825 milliamps. Fallon. So we've got node A, node F. Okay. 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 What is that current also? That's our total current. Correct.
So, wait, how do we get 50? Is there something that's exiting?
This is the only one that's exiting. We have 54.825 going in, and we have the 3.75 that's going in.
Oh, I thought that was 6. Oh, okay, I was looking at the wrong thing. 3 something, okay.
So yep, again, so we add up the currents going in through R1, and we have the current coming from our load A converging at that point, gives us the 58.575 milliamps, which is our mainline current, our total current. That's also going to be the current flowing through resistor 5. Oh, let's change that music. That's one we haven't used. We are solving for either node F or node G. Take your pick. Okay. So what do we have going in? What do we have going out of G? Okay. Okay.
The number
325. Yep, just like it's supposed to. And I killed it. Okay. So now that takes care of node F as well, because that was the only other current we were missing. It was a trick question. So now all of the nodes are taken care of. We have all the current paths. We know where everything is going. We've accounted for it all. So now, Max, what is the value of R1?
R1 is 6 volts divided by 54.825 109.439 ohms.
I agree. Because at this point, that's the only thing that we have left. We have our current, we have our voltage. The only thing is to find it. Jeff, value for R2. And our voltage is the 3 volts. The what? No. So you have your 3 volts divided by the 51.825 milliamps. Yep. 57 ohms. Jeff, you got lucky again. R3. Yep. R4. Yep, 17 volts divided by 27.325 milliamps. Correct. Hmm? This current, the current that we had coming up through here, which is the 27.325. Yeah, 17 and then the 27. And our last one. Dylan, you're just going to burn all yours up in the first day. Okay, R5. Everybody agree with those? Yes, it is.
Did I calculate that wrong? I just wrote it down wrong.
300. Yep.
That's on the scope. That's on
So 341 ohms. Okay, and now the bonus round. Bonus round. Morgan, what's our total power? Watts. So across all those resistors, we're going to be spending about 4.6 watts. It's not terrible. You know, for a total current, I think the biggest one where we would have, so biggest voltage, biggest current, would probably be this guy here, our RLC. That's probably gonna that's gonna have the most power. Okay. We did. That's because we went through each individual little answer. When I stopped you guys, we were right at 20 minutes. So that was right at the quiz length. Okay. Do you guys have any questions about how to solve for these guys? Well, yeah, you'll be looking for pretty much these guys. Yep. The power total is what I added on at the end. Okay. Go through the quizzes. If you guys have questions, bring them up tomorrow. Tomorrow we will review. We'll kind of cover everything that you guys have questions about from this week, and we'll cover any questions that you have from last week's material for the test. We got one, and we'll have one topic we'll just cover tomorrow is more troubleshooting. As far as
like, say if I had like one assignment that I wasn't able to unlock before the test.
So you have to get all the assignments done before you can take the test, and then the test closes on Sunday night.
Okay, so then that means that I will have lost those points.
Yes.
Gotcha.
Yep. If the test isn't completed before that deadline, yes.
Okay, so then let's say if okay, so it's more so with lab where it's like a bit easier.
Yeah, lab's a little more lenient as far as the due dates go.
Okay, so should I focus a bit more on theory in terms of getting?
Yeah, get the theory done first.
Okay.
Lab will follow what we're doing in theory. If you don't understand what you're doing, you can't do the practical application.
Also, thank you so much for your help the other night. I'm sorry that I kept on blowing up your phone.
No, you're good. This is what I'm here for. That's why I give out my information.
It was bad though, because I was wondering, I'm like, how in the heck did
So it looks like you were just fat fingering something into your calculator for the parallel resistance. Because everything else, as far as what you did, the theory behind it was correct. You just had the wrong values. So take that, take that as a win, that you're understanding what you're supposed to be doing. You're just getting one, obviously at the very beginning of the problem, but the rest of it you understand.
Okay, yeah, I think too I might get a different calculator because these are really hard to check how many parentheses there are.
Yeah.
So yeah, that's something that I'll work on.
Lots and lots and lots of parentheses.
If I have too many though, then it's like, syntax error. What do you want me to do?
Yeah. Well, if you put too many in one direction, if you put too many, it doesn't care. I can't remember which side of it is, but if you don't put enough, it gets pissed at you. But if you put too many, it doesn't have a problem.
Okay, I think I might get something because I've been using an online calculator called Desmos where it kind of like lays everything out for you. So
Yeah.
I'll see if I can find something like that.
Honestly, the TI-83, TI-89s. Those. Mhm.
Oh, I thought only the 84.
Oh no, they got tons of them. So like, let me show you. Oops, I guess I should stop this.